Hello everyone. In this video we'll be talking about the mirage. There are a lot of misconceptions about the mirage, and the biggest one is that mirage is the example of total internal reflection. We'll destroy all such myths in this video, and then we will see two famous categories of the mirage, the inferior mirage and the superior mirage. So let's begin. On the left hand side of the screen, you will see the misconception, and on the right hand side, you will see the truth. The biggest misconception, as I told earlier, is that mirage is an example of total internal reflection. But the truth is, mirage is an example of the refraction. Okay. Another misconception about the mirage is that it is an optical illusion, but the truth is mirage is a real optical phenomenon. Next misconception about the mirage is that mirage cannot be photographed, but the truth is mirage can easily be photographed. And the next misconception is that mirage cannot happen in the night, but the truth is mirage can happen anytime. Okay, so we'll now see the definition of the mirage, and then we will see the two primary types of the mirage in the detail. Here you should pay attention to the highlighted words. Number one, mirage is a real optical phenomenon. Number two, it is happening because of the refraction. Number three, most important, there will always be an inverted image, at least one inverted image formed by the mirage. Okay, note down this definition, and here you can see the type of the mirage. The famous two types we will consider, although there are plenty of the types of the mirage. You can Google about them. Once you understand the inferior mirage and the superior mirage very well, then you can understand all the other types of the mirage very easily. So I am starting with the inferior mirage. Suppose this is a hot sunny day, and due to the intense heating by the sunlight, the surface has more temperature as compared to the environment above it. So this air I am writing as hot, and comparatively here we have the cold air. The hot air will have the less refractive index, and the cold air will have the larger refractive index. Okay. Now consider a ray of light traveling straight toward the eyes of the observer like this. Another ray of light I am taking like this, which is initially headed toward the surface, but practically this ray of light bends toward the upward direction. This bending can be explained only using the wave nature of the light. Using the geometric optics or the ray optics, this bending cannot be explained. How? Let's check it here. Suppose this is the wave front of the light. This red is indicating the wave front, and this is the light ray. Okay. Here the air is cold. It means larger refractive index. So this part of the wavefront will be traveling slow, and here the air is hot, so less refractive index means this part of the wavefront here will be traveling comparatively faster. It means in time interval t, when the stop point of the wavefront reaches here, the bottom point will travel more distance, the greater distance. So that bottom point might reach somewhere here. It has traveled greater distance. So this is the new position of the wavefront. Do you agree? Okay. After some time t, again if we check, this top part of the wavefront will reach somewhere here. Then this bottom part will travel comparatively more distance, and that will be reaching somewhere here. So this will be the wavefront. Again after some time t, we check the wavefront. This top part is moving slow, so it will be reaching somewhere here. The bottom part is moving faster because here the refractive index is less. So this part will reach, let's say, somewhere here. Now you see the different orientations of the wavefront. You have read it that in the wave optics, the light wave travels perpendicular to the direction of the wavefront. So if you check all these wavefronts, you'll get the idea why the light is bending upwards. Okay. Using the geometric optics or ray optics, this bending cannot be explained. I'll tell you the details. Now, for this observer, this ray of light will appear to be coming from somewhere here. So, for this observer, here will be an image of that tree. Okay. This image will be unstable because the hot air has a tendency to rise up and the cold air has a tendency to move down. This will cause the intermixing of the different layers of the air and which will result into turbulence, and that will distort the image. Done? Why we use the name inferior mirage? That can be explained using this image. The image formed here is below the real object. That's why we call it inferior mirage. Okay. Now, suppose we use the ray optics to explain this bending, and we draw the ray again. At the lowest point of this trajectory here, pay attention, I am making a normal and a horizontal line. Okay. This part of the ray is making how much angle of incidence? This part which is very close to the blue point. If you think carefully, the angle of incidence will be 90 degree. If angle of incidence is 90 degree, then angle of reflection should also be 90 degree. It means this angle should also be 90 degree. Okay. If the angle of reflection is also 90 degree, the light ray should travel straight like this. It should not bend upwards. Getting the issue with the ray optics? Why ray optics is getting failed here? I am explaining that. Focus on this blue point again. Consider here a layer of air. The thickness of this layer of air will be very small. Okay. Since this layer has a thickness lesser than the wavelength of the light, it means in this layer the propagation of the light cannot be explained using the ray optics. But using the wave optics, using the wave theory of the light, we can explain this bending. If we consider the light as a wave, the wave will have amplitude. Okay. This wave will sense the gradient of the refractive index, and then using the Higgins wavelet, we have already proved, Higgins wavefront, we have already proved that this light ray will bend upward. Okay. If you check the radii of the wavelets, here will be comparatively less radii, smaller radii, and here comparatively the radii will be more. The reason behind that is simple. In the less refractive index, the wavefront will have greater speed. So these wavelets will spread faster. That's why this point is traveling more distance in the same time interval as compared to the top point. Okay. It's the simple explanation for the inferior mirage. Now you can see the entire theory on the board, and then I'll be showing you few images where the inferior mirage is observed. You may pause the video there and you may ponder about those images. You'll get the better idea of the inferior mirage. Another beautiful example of the inferior mirage is the presence of the water on the road during the hot sunny days. See the explanation here. Suppose this is a road and here the air is hot. Okay. The light coming from the sky will actually bend upward, that we have already seen. And suppose here is some observer. Now for this observer, this ray of light will appear to be coming from somewhere here. So here will be actually an image of sky. But this image of the sky, as perceived by the brain of this person, will appear as a patch of water. Okay. As we had the talk that cold air has a tendency to move down, the hot air has a tendency to rise up, and there is intermixing of these air layers which causes the turbulence. So this image will be unstable and then brain will perceive it as a patch of water. As the observer reaches at that location, he will find that there is no water. It's a famous type of the inferior mirage, also known as the road mirage. Okay, explanation is the same. In the hot air, there will be the less refractive index of the air. In cold air, there will be the more refractive index. And the wavefront here will travel faster. Here the wavefront will travel slower. So if I consider this as a wavefront, this part of the wavefront will be traveling slower. So after some time, let's say this part reaches here, but this bottom part will be traveling faster. So it might reach somewhere here. Okay. So the wavefront will get tilted. Again, after some time, this top part of the wavefront, let's say, reaches here, but the bottom part will travel comparatively more distance as it is moving faster. So the wavefront will look like this. These are the wavefronts. After some time, if you check, this top part of the wavefront, let's say, reaches here, but here the bottom part, due to the less refractive index, will be traveling faster. So this point might reach somewhere here. This will be the wavefront. So using the Higgins wave theory, you can see the wavefronts are continuously bending like this. So this ray bends upward. Okay. Now let's talk about the superior mirage. They happen when the air below the line of sight is cold as compared to the air above it. So let's consider the example here. We have some observer and there is a ship. Now this air is bit cold. So here we will have more refractive index and the air here has more temperature. It indicates the less refractive index. Okay. A ray of light coming from the ship will not travel straight toward the observer like this. Actually, the refractive index is varying continuously. So the light ray will bend downward like this. This downward bending can easily be explained using the Higgins wave theory. Suppose you consider a wavefront here. Then we know that this point of the wavefront will be traveling faster because here the refractive index is less. And this point of the wavefront will be traveling comparatively slow because here the refractive index is more. So after time t, if you check, let's say the red point reaches somewhere here. This part of the wavefront reaches here. Then this part will travel up to here and this is the wavefront. Now after some time, this point might reach somewhere here, but this point is traveling slow, so it might reach only up to here. This will be the wavefront. Okay. After some time, if you check this point, let's say might reaches here, but this is traveling slow, so it might have reached only up to here. This is the wavefront. So you can see there is the bending of the light ray. Okay. This profile is known as the temperature inversion because usually in the daytime the air nearby the surface is hot and the air above it is usually cold. The image perceived by this observer will be actually inverted. For this ship, this observer will perceive an inverted image here. These superior mirages tend to be more stable as compared to the inferior mirage. Can you guess why? This is more stable as compared to the inferior mirage. The logic is simple. Cold air has no tendency to go up and the hot air has no tendency to come down. So there is stability in the air layers. Due to that, this is more stable. Okay. I hope you enjoyed the information, and if you want to explore more such beautiful informations, you can go through the remaining playlists and ask your friends about the knowledge of the mirage. Check whether they know it or not. Stay awesome. Take care. See you again.